on 3.1 and 3.2, derivative of function and differentiability. The derivative of function f with respect to the variable x is the function f prime whose value at x is. So we're saying we're taking the derivative of f prime, which is usually the equation f of x right there. Make sure you notate the little prime right there. If not, then we're assuming it is the original equation. And then we are also saying that in respect of x, so wherever there's an x variable, we're taking the derivative of that. Now this also right here should look very familiar to us from chapter 2. In chapter 2 we had to find the slope using the limit as h approaches the 0. Same idea right here. We're going to take the limit as h approaches 0. Instead of a plus h minus f of a, we're going to substitute that with the variable of x instead, because we're going to use the x to figure out if it is differentiable or not. Now we say that f has a derivative, or if it is differentiable at a point of its domain. So wherever there is an x, remember x is the same as domain. So if it does exist, then we're saying at that value of x right there, it is differentiable, or you can take the derivative of. So we also have to talk about the notations of derivatives. There are several ways to notate if we're taking the derivative of something. One of the things that we're using is a y prime, because a lot of times our equation is going to be written as y equals, so we're going to have as y prime. Make sure again you put that y prime to notate that you're taking the derivative. If you don't, then I assume it's going to be the original equation. The other one we're going to be using is dy over dx, meaning that we're taking the derivative of the y equation in respect of x. So we're taking the derivative of the x variable. The other one is df over dx. The df is because sometimes our equation is written as f of x, which is the function, right? So we're taking the derivative of f of x, again, in respect of x, meaning that the x variable are the ones that we're taking derivative of. And then the last one is the derivative of f of x is how this notation works. Okay? Now normally in this class we're going to use these two right there, the y prime and the dy over dx, because most of the time our equation is going to be written as y equals, but sometimes if it is written as f of x, then we'll use this notation as well. Alright? We're also going to prove that something is differentiable by using what we call the one-side derivative. So one side that we're going to prove it at is the right-hand side. If you remember again, the limit as h approaches the 0 of the plus right there, that's the right-hand side. We have done something like this where we said, does the limit exist on the right-hand side and also on the left-hand side? If the numbers were the same, then it exists. If it's not the same, then it does not exist. So similar to this, on the derivative, we're going to see if it is differentiable at x equals by taking the right-hand side and also the left-hand side of it. So in this case right here, we're still using that f of a plus h minus f of a, or again, we're going to substitute in the x's in replace of those a's right there. I'm using the variable a right now just to show that this is the right-hand side. That's the only reason. And then on this same thing, from the limit as h approaches 0 from the left-hand side, I'm using b just to show that it is from the left-hand side. But again, we're going to substitute in the a's right there with a number and the b's with a number instead. Okay? So again, this is very familiar. It's almost like we're putting the limit, does it exist, and also finding the slope. We're putting those together and finding if it is differentiable. So let's take an example 1. Example 1 is then our x squared, which is that parabola shape that we know. And so I have the little parabola shape going right here. And this is when x is less than or equal to 0. So using this piecewise right here, this restriction says take only the parabola shape when x is less than or equal to 0. So that's this part right here. Okay? And then the other one is the 2x is the linear equation that we know. And again, we're only taking that linear equation when x is greater than 0. So in this case right here, this is our linear equation when x is greater than 0 right there. Okay? So using this now, we're trying to prove if it exists or if it's differentiable at the point of x equals 0. So where those two graphs meets right there, is it differentiable? Okay? So now we have to take it from the left-hand side. So I'm going to take it from the left-hand side and using this equation, so this is similar to finding the slope. If you remember finding the slope, we take that equation and we mimic that and we substitute in a plus h minus f of a. Well, instead of a plus h, we're going to use a as my x value right here. So that's the 0 that I substituted in. Because again, we're trying to prove it at x equals 0 right there. Okay? So we substitute in 0 right there for the a, and then substitute a again with the 0. So this right here, if I simplify this, is going to leave me at h squared over h right there. And again, we cannot substitute in 0 into this place right here, because then you're going to have 0 over 0. So we don't want that. We want to make sure we simplify the h as much as possible before we can substitute h of 0 right there. So in this case, I'm going to be left with just an h because the two h's will cancel out, from one from the top, one from the denominator. So then if I substitute h then at the end, we're going to have 0. So on the left-hand side, when we take this equation right here, we're saying it is going to come out to the value of 0. Okay? Now let's try from the right-hand side. So again, now we're taking this 2x, we're going to mimic that equation on the right-hand side, and we're going to do 2, and then the x right here is going to be substituted with our usual, the a plus h's, but again, the a, we're substituting the x value of 0 right there. So we put in 0, and then minus 2 times 0 again, because that's our x value that we're using for that part. Okay? So, if I simplify this right here, again, this right here, 2 times 0 is 0, 2 times h is going to give us 2h minus 2 times 0, so those zeros are gone, and we're left with h over h. Again, in this case, do not substitute in 0 for h, for the h value of variables, because then that's going to give us 0 over 0. So instead, you want to reduce this. So, as we reduce this right here, we're going to have the value of 2 in this case. Okay? So, similar to the equation or the problem that we did for does the limit exist, we did the right-hand side and also the left-hand side of the limit. And if at that place the numbers were the same from the right-hand side and the left-hand side, the limit exists. So similar to that idea, on the left-hand side and the right-hand side of the derivative, if it's the same, it is differentiable. If it's not the same, then it's not differentiable. Okay, so that's what we're going to do today, is figure out if at that place, a certain place that is given, if it is differentiable. So you have to take the left-hand side and also the right-hand side, find the value for the left and right, and see if it does exist or does not exist. Okay, now that's one way to prove if something exists. So similar to our limits, does it exist? That's one way to prove it. The other way to prove something, if the at that point, if it exists, if the derivative exists, is by looking at it graphically. Okay? There are 4 cases of this where it does not, if it's not differentiable. One of the case is going to be at this right here, the absolute value. Normally this V shape right there is the absolute value right there, and it does not exist at x equals 0 where those 2 lines meet right there. It does not exist. Okay? So we call this shape the corner right there. At that corner right there, it does not exist, or it's not differentiable. Right? The second shape that we have is this thing called the cusp right here. Okay? So basically the cusp is when positive infinity, the graph of the secant line is coming from positive infinity, it's coming this direction, and then also from negative infinity if it's coming from this direction, and it meets at this place at x equals 0 right there. This is called the cusp right there at that location. Okay? And we're saying it does not exist, or it's not differentiable at that place of where the cusp meets at right there. Now there is a difference between the cusp picture and also the corner picture right there. This is more of that sharp shape right there, which normally is found from the absolute value of x right there, that V shape. And this right here is a different equation, so it's a little bit more rounded or curved, and that's going to be meeting right there at that cusp. Okay? The third shape is the vertical tangent. So again, this is coming from positive infinity right there, and this is coming from negative infinity, and the graph is going to meet right there, and it's almost like a vertical line right there that's going to create right there. At this place right here, we're saying it's not differentiable at that place right there for the vertical tangent. All right? And then the last graph is any type of discontinuities, then it does not exist. And if you remember from chapter 2, we went over 4 types of discontinuities. One of them being the removable discontinuities. Then the other one is the jump, which is this picture right here, is the jump discontinuity. We also mentioned about the infinite discontinuity and also the oscillating discontinuity. So any of the 4 types of discontinuities that we mentioned in chapter 2, then it does not exist. Okay? So graphically, by looking at the graph, we can determine if it's differentiable by the 4 cases that we have. Also, we can prove algebraically by doing the left-hand side and also the right-hand side of this. Okay? So that's what we're going to work on now, is going to find out if it exists or if it's differentiable at that place, and then again, we can determine the type of the non-differentiability by the 4 cases that we have.